Okay, so real numbers are any number that you can put on a number line. What real numbers are not are any number like square root of -4. Anytime you have the square root of a negative, that's going to be imaginary. So we haven't learned about imaginary numbers yet. We will. As long as there's no square root of a negative, that is going to be a real number. So pretty much everything else that we'll deal with, every number you've ever seen in math class to this point has been a real number. Oops. So rational numbers. So rational numbers, sometimes students forget what these are. You can talk about this in terms of a decimal if you wanted to. And so if you talk about it in that terms, there's two ways to define it. You could call it a repeating decimal. Rational numbers have a repeating decimal. Or terminating. Terminating means stop. So like 0.3 repeating is rational. 0.5 is terminating. Or another way of describing rational is this word fraction. The fraction of integers. In fact, that's probably the best way to describe a rational number. So when you see the word, in Algebra 2, we'll see this a lot. When you see the word rational, it's kind of a code word for fraction oftentimes. And you can see that this is equal to 1/3. This is equal to 1/2. Right? Any repeating or terminating decimal can be written as a fraction. So that's really a better definition of that. So even a number like 5, right? 5/1 is 5, so that's rational. Irrational is a number you can talk about two different ways. Again, you could call that, let's talk about the decimal first. So the decimal of that is either non-repeating, so it doesn't repeat, and non-terminating. So the most famous one, most famous irrational number would be pi. Right? We know that they've taken that out millions of places, billions of places, and it doesn't ever repeat, it doesn't ever stop. But less famous, but still nice ones are square root of 3, square root of 2. Square root of 4 is actually not irrational because that's equal to 2. Or cube root of 5 would also be, anytime you have square root of a non-perfect square or cube root of a non-perfect cube, you would have an irrational number. So let's organize this into a Venn diagram. I think it'll help us. So all of these numbers here in this rectangle are real numbers. In this rectangle we have our imaginary numbers. And there are two types of real numbers. There are rational numbers and irrational numbers. A type of rational number is an integer. Integers start counting, like it can be negative, -2, -1, 0, 1, 2, ... Keep going. Whole numbers are a type of integer. So whole numbers start counting at 0, 1, 2, 2, and so forth. And then natural numbers or counting numbers are even a smaller subset of whole numbers. So that starts counting at 1 and 2 and 3 and so forth. Okay, so let's pick out a few numbers and put them here. So negative square root of 7 is going to be irrational, right? It's not a perfect square. 2 plus 5. Even if I add a rational number to an irrational number, it's going to remain irrational. Pi is irrational. 2.35 is repeating, so we know it's rational. We know it's a fraction. Square root of a negative would be imaginary. 0 is definitely an integer, but even better, it's whole. So I want you to understand how this works. So 0 is a whole number, and an integer, and rational, and real. And if we wanted to go to the bigger overarching category there, all of these numbers real and imaginary, are part of the complex number system. So every number you've ever heard of is complex. In fact, some numbers are specifically called complex, like this one. Has a real part, 5, an imaginary part, 2i. This one would be rational. This would be, see, that's really 11 in disguise, so that's a natural number and whole, and integer, and rational, and real. And finally, the last one, this may not look familiar. It's a more famous number than pi for mathematicians, but you haven't learned it yet. It's called Euler's number, and it is irrational. Expressed as a fraction. So we're going to take this and express this as a fraction. So we're going to call this x equals 0.08. Now some of you might know the answer already. There's a shortcut you might have learned in elementary school, and you know, oh, that's just 8 9. Let's learn a way to do this by hand without using a calculator, how to express this as a fraction. Any repeated decimal can be written as a fraction. So if I do something to the left-hand side of this equation, it's kind of unusual. I'm going to say 10 times x. If you multiply this side by 10, to be fair, I get 8.8 repeating. Now the nice thing is now I have a little equation I can subtract. I get 9x on the left. And what happens here on the right is the 0.8 minus 0.8 is 0, right? So we get 8 on the right. So divide by 9, and we get our shortcut answer of x equals 8 9. Let's try this one. Very similar. So we're going to start this. Yeah, I like to start that number. So okay, x equals 0.37 with the 7 repeating. So we'll say 10 times x equals 3.7. That should be. Move the decimal place over 1. Now the 7 repeating is in the same spot there, so that will nicely subtract away when I subtract these two things. So I'm going to subtract, I get 9x equals 3.4, it's 3.7 minus 0.3 is 3.4, divided by 9. Now I have trouble sleeping with that fraction. I don't like decimals and fractions to be in the same, really mathematicians don't like that. So we're just going to do a little adjustments here, maybe multiply top and bottom of that fraction by 10. And when you do that, you get 34 over 90. Again, I still want to simplify that just a little bit there, maybe take out a 2, 17 over 45, and I've got my answer. So if you type 17 over 45, you'll get 0.3777 repeating. Okay, so we're going to do our method here, and we go x equals 0.83 repeating. We know that's 83, 83, 83, 8 and 3 repeating. And the problem is, don't do this, but watch me for a second. If I multiply by 10, something weird happens. I get 8.38 repeating. Now those don't subtract nicely. This is not going to work. I can't multiply by 10 and really get this thing to work. It makes sense if you think about it. We've got 2 decimal places there. So instead of multiply by 10, let's multiply by 100. So we get 83.83 repeating. Now you see when you subtract, you get 99x equals 83. And those cancel, or at least subtract to get 0. And we get x equals 83 over 99. And in fact, some of you knew the shortcut. Some of you knew that was 83/99. That would be a little quicker if you did it that way. Okay, so let's talk about interval notation here. And open and close. Let's start with open and close. So open is, this guy is open, does not include -2. Closed means this 3 there is closed. It includes the value at 3. So this guy is open, and this guy is closed. That's the terms we're going to use to talk about that. Inclusive is this. that value is excluded there. So bounded and unbounded. So this is closed, open, closed, right? Bounded and unbounded. So let's talk about that for a second. So this is a little harder for students. Unbounded means it goes forever in one direction. It goes forever. It doesn't stop. The graph of that guy would go on forever. This graph has a starting point and ending point. It is bounded. This graph goes on forever to the right, forever to the left. It is unbounded. This one goes forever to the left. It is unbounded. It goes in one direction. That's all it has to go to be unbounded. It goes in one direction forever. Now let's talk about the way we represent these graphs algebraically. So if I'm going to represent these algebraically, I'm going to teach you a new thing. It's called function notation, or interval notation. Interval notation. Looks like this. You're going to have a lower bound, comma, upper bound. Always put the smaller number first. So in this case, the smaller number is -2, so we'll say -2, comma. The upper bound would be 3. And because this is a closed circle, I'm going to put a hard bracket here. Closed circle, hard bracket. Open circle, parentheses. And that is interval notation. Now, you've also seen inequality notation. Inequality notation looks like this. It would be -2, and x is in between -2 and 3, less or equal to 3, less than -2. So that looks like inequality notation for that problem. You've probably seen that one before. This is probably new. So this one, let's take just the left-hand side of this. What's the lower bound? The smallest number would be -infinity, comma, the upper bound would be -1. It's a closed circle, so hard bracket. And infinity is not really a number, it's an idea, so it's not a firm starting or any place, so we're going to always use parentheses anytime infinity or -infinity is involved. So look at the right-hand side here. We get 2 as the lower bound, infinity is the upper bound. Infinity always is parentheses, and 2 is open, so that's parentheses. We're going to come back to that in just a second. Let's write this in inequality notation. So this is x less than or equal to -1. X is greater than 2. And either or are true, so we usually use an or statement there. Now, an or statement in this, we always write it the formal way, which this symbol means union. The union between those two sets. It's an or statement. And here, inequality notation would be x less than or equal to 0. And here would be -infinity, comma, 0. Bracket at 0, parentheses always for infinity, -infinity. Let's represent a couple of these. We use at most 5. So at most 5 means 5 or less than that. Let's do this one. So 1, 4. It says at least 1, includes 1 or bigger, but less than 4, something like that. So inequality notation, that would be 1 less or equal to c less than 4, or we could just say 1 comma 4, parentheses, because open, closed, so hard bracket. Let's do these last two, or at least this last one here. -2 and 5. So I'm going to put my thinking up above for a second here. So this one is x less than 5, and this one is x greater than or equal to 2, and means the intersection of those two ideas. So my final solution is just from here to here. So that's my final graph. Those are just to show a little bit of work.